So we're recording, so that's looking good. Just a second. Okay, so I've marked the correct answers for 1 through 11. So you should have those on your test. For 12, the amplitude is 15.3. The angular frequency was 1.25. The phase angle was pi over 2 or pi over 5. The frequency is 1.25 divided by 2 pi, and if you calculated it out, you still got credit. The period is 2 pi over 1.25. The graph, the magnitude, if you look over on the scale, the big lines are 2, not 6, not 4. They're 2. So the amplitude was 3. The period was 2. If the period was 2, then the frequency was 0.5. So the angular frequency was 2 times 0.5 times pi. So the angular frequency was pi. To find the phase angle, you had to set cosine equal to 0, which means it was going to be 90 degrees, which in radians is pi over 2. And so your equation should have been x is equal to 3 cosine pi times time plus pi over 2. The spring had an initial length of 5 centimeters, a force of 4 newtons. Force divided by its stretch, and stretch needed to be in meters. And that was going to be, the stretch is 25 centimeters minus 5 centimeters gives you 20 centimeters, which is 0.2 meters. So you end up with 4 divided by 0.2, which gives you 20 newton meters. Lots of arithmetic errors on that one. I had people just did something weird with the arithmetic. The bead traveling around the hoop at a frequency of 20.5 hertz. The period then becomes, because it's 1 over the 20.5, becomes 0.49 seconds. If you wanted to calculate the period, but if you just wanted to calculate the angular frequency, it's 2 pi times 20.5, which is 128.8. On 16, that was exactly like what we had in the quiz. X of t is the amplitude times the cosine of omega t. So if the amplitude is 5, omega is 1.75, the velocity became negative 8.75 sine of 1.75 t. The acceleration became negative 5 times 1.75 squared, which became negative 15.31 cosine of 1.75 t. The 17 was just like the quiz, that omega is equal to the square root of the spring constant divided by the mass, except this time the spring constant was 32, the mass was 2 kilograms. 32 divided by 2 is 16, square root of 16 is 4. So the frequency is 4 divided by 2 pi, which means it was 2 divided by pi. And I saw a lot of pi's in the wrong spot and the 2's in the wrong spot. Okay, I was trying to avoid these, but we're going to go ahead and go to the document camera. See if it will show up. All right. If I'm drawing the third harmonic of a pipe that has both open at both ends, I end up with 3 half wavelengths. Some of you got that right, but you gave me the 3 half wavelengths with the nodes at the end. That's for a closed pipe. For an open pipe, you have to have the antinodes at the end. So my third harmonic, 3 half waves. I was looking for infrasonic, audible, and ultrasonic.
That was the sad part.
And the ones, and most of you, let me tell you, you overthought it big time. Same with this one. Transverse waves are like in a string, have a displacement from the vertical. Longitudinal waves are like a slinky, where I'm going to get rarefication and condensation, rarefication, condensation. Huh? Just a second.
So I kind of, you said that transverse waves were with the string or longitudinal?
Transverse waves are like the string. Longitudinal waves are like in the slinky. Longitudinal waves are sound. Transverse waves are in a string. 18, that's your pipe. Antinodes at the open ends.
So how will it close end of the pipe look like?
The closed end, it'd have a node in it.
Oh,
Yeah, closed ends have nodes. So I can have one open end, if I did one open end and one closed end, that's what I would describe. And then, like I said, I think I marked the correct answers for the multiple choice. Okay? All right, let me go over to the computer real quick. Now that it looks like everybody's here that's going to be here today. Test will be next Friday, and it'll cover Coulomb's law, electric fields, and electrostatics. I have provided for you in week 5. I have a whole bunch of extra stuff to help. Okay? So if my explanation doesn't work, hopefully one of these explanations will work. And I could have guaranteed it was going to rain. I could have put money on it because it's electrostatics day. It's wet outside. Makes it a pain in the tushy. However, it's wintertime, and inside the buildings, if everything's working, which apparently it is today, I get dry air. Yay! But that did make it a trick to bring over my rabbit from the science building. I made sure it was stuffed in the sleeve of my jacket so it stayed dry, because otherwise I'm going to have a real hard time with today's demonstrations. So you've got some history back there. We've got playing with static electricity. We've got UCLA's Coulomb apparatus. We've got a Coulomb's law class video. I've got, if you guys haven't discovered the organic tutor guy yet, let me tell you, the organic tutor guy is great. He does more than organic chemistry, but that's how he started, was doing organic. And he's got a lot of good stuff, but he's got Coulomb's law. We've got Coulomb's law, net charge, electric fields, and I have the charges and field simulation pet thing that's already embedded in Blackboard. So you've got lots of stuff. And then we start with electric fields and electric flux. And that's probably about as far as we're going to get before the test. I doubt we'll have electric flux on the test, because what we'll do is we'll start today, we'll get Coulomb's law today, we'll work Coulomb's law problems on Friday, and then we'll probably work electric field problems next Wednesday, which gets us to the test next Friday. And then we've got some Gauss's law problems in there. So this will get, you've got lots of extra stuff in week 5. So totally a lot of extra stuff in week 5. Now, let's see if I can get back to the TV camera. I really want to quite think that. There we go. Okay, so what we're about to embark on is just as much history and philosophy as it is the actual science. Electricity and magnetism, which is the heart of physics 2, gets us from static electricity all the way up to electromagnetic waves, which is why I start with mechanical waves at the beginning of the semester, and then we end up with electromechanical waves at the end. And hopefully with time we do optics, because optics is incredibly important in a lot of your instrumentation that you end up using. Most of you have had general biology by this point. Most of you have had microbiology, or you're in microbiology right now at this point. And one of the tools that you use is what?
Compound light microscope.
Compound light microscope. That's all optics, okay? Microscope is all optics. So optics is a big deal. Optics is a huge deal because a lot of our instrumentation all deals with optics, all deals with electromagnetism. Things like your GCMS uses an optical detector. We detect frequencies with our detectors. We use light scattering to detect particle size. We use electromagnetic fields for a lot of different things. And so a lot of the instrumentation that we end up with is really, really critical. So how we teach electricity is almost both philosophical and historical, because electricity caused a lot of different consternation as we were doing it through the science. So if you think about it, who were we taught that discovered electricity? Back in elementary school, somebody said, this person discovered electricity. Who was it? Benjamin Franklin. Well, that's not exactly right, as most things are in science, right? It's not exactly right. But Benjamin Franklin did coin a few things that helped us explain electrical flow. But electricity it was an observation that people had observed a long time before that. It was, could we actually generate it? Where did it come from? How could we contain it? And how could we explain it mathematically? And we will all grow to hate Benjamin Franklin because he got it wrong. He got it wrong. He got the charge carrier wrong. And so we, to this day, do everything backwards because he got it wrong. So we talk about Benjamin. Now think about when Benjamin Franklin lived. It was when? 1800s, right? Died in early 1800s. So if you think about that, that's only 250 years. We're not talking a whole long time here. And in fact, electromagnetic waves and electromagnetic wave theory was fought over the late 1800s, early 1900s. So you start thinking about that, you start thinking about the time frame of what we're talking about, which is why physicists weren't called scientists until the early 1900s. They were considered natural philosophers because they were trying to explain things. So what happens to us with electricity and magnetism is that we start out with observations. We're going to do observations with electricity. We're going to get up with good old Coulomb. We're going to look at things with Volta. We're going to look at a variety of different folks. And we're going to start putting the pieces together to end up with Faraday and end up with Maxwell. We won't go as far as Einstein, but we end up building on those observations. So we're going to start with the first observation. So let me ask the question. What is electricity?
Flow of electrons.
So I got somebody who says flow of electrons. Anybody else have another thought as to what electricity is?
Is it, the charge of electrons that have magnetic field?
So I got somebody that says charge on the electrons that gives us an electromagnetic field. How about you guys over in Enid?
Flow of electrons due to potential difference.
We got a flow of electrons due to a potential difference.
Does it have anything to do with static?
We got talking about static. All of those things go into what we call electricity. Okay? All of those things go into what we call electricity. Now the flow of electrons we actually call current. Static electricity doesn't deal with current, right? Static electricity does not deal with current, but the flow of electrons does give us current. So that's one thing that's in there. And we get a charge on the electron. That's what the Millikan oil drop experiment gave us, is that we get a charge on the electron. We can measure it because it's quantized, meaning that if I have an oil drop that has 10 electrons on it, it's going to have a charge of a certain magnitude. So we got, so it's quantized, and we can actually measure the charge on an electron. That's what the Millikan oil drop experiment does. We balance the forces in order to figure it out. So we get that part of it. So we know, and that's where Benjamin Franklin got it wrong. Benjamin Franklin got it wrong because he said that electricity was driven by the positive charge carrier. That's where he got it wrong. He defined the flow when we dealt with electricity. He based everything off of the positive charge carrier. And we now know that that's not correct, right? We know now that it's the negative charge carrier, which is our lovely little electron. Electrons are special, right? Electrons are special. They're spherical, number one. We found that out about 4 years ago. Think about that for a second. We've known about electrons for a long time, and we just found out 4 years ago that they're spherical. Think about that. Electrons, and electrons and protons are different, because when we get into magnetism, one of the things that we know about magnets are I can break a magnet in half and get two magnets, right? I can break that magnet again and get two magnets. I can break it again and I still get two magnets. I always have a dipole when I have a magnetic field. Always have a dipole. There is no such thing, at least as we know right now, although there are people that are out there saying Mother Nature is symmetric, and because Mother Nature is symmetric, there should be a magnetic monopole. We should be either able to find a magnetic monopole, or we should be able to create a dipole in an electron or a dipole in the proton, which we cannot do. So depending on which side of the research you go on is where you're at on that one. So you either are looking for the magnetic monopole, or you're trying to create a dipole. But to date, we have not created a dipole in an electron. And my electron is negatively charged, and my proton is positively charged, and Ben Franklin got it wrong. So we end up with that. So how we historically start talking about electricity is we talk about electrostatics. And we're all familiar with electrostatics. What is the primo example of electrostatics?
The little.
Sound? So somebody said sound. What did you think, Thomas?
The little ball that makes your hair stand up.
Little ball that makes your hair stand up. That's the Van de Graaff generator. Van de Graaff generator can demonstrate electrostatics, but there's a bigger example that we're all familiar with, and you've probably been experiencing over the last month. If you wear socks across a carpet and you go to the doorknob, what happens?
Shock.
You get a zot, right? You get a zot. Now, have you guys done Van de Graaff generator in the lab yet? Okay. Well, I will tell you, it always fails for me because it's always raining. And I can almost guarantee you that when I do physics 2 in the fall, or especially over the summer and in the fall, we're not in winter time. So the building is cooled instead of heated, which means there's more moisture in the air, which means my Van de Graaff generator doesn't work so hot. It's a pain in the butt. Cannot demonstrate static electricity without the Van de Graaff generator. Well, you can. But even the demonstration I'm going to do today doesn't work so hot. Okay? It's going to work okay today. But I will tell you one of those things, everybody fingernails on a chalkboard? People familiar with fingernails on a chalkboard, even though we don't have chalkboards anymore? That sound drives some people crazy. It's the crackle of the Van de Graaff generator that drives me absolutely insane. That's one of those things that just gives me the heebie-jeebies. So we're going to do static electricity, and I'm going to do it on the document camera. So, good old static electricity. The other primo demonstration of static electricity, what I've got here is I have good old rabbit fur. I have a balloon, and I can rub my balloon on the rabbit fur, and I can actually, even though we won't hear, you can hear it around the room if you pass around, I can get the crinkle of the static electricity on the balloon. And if I do this, you can actually see if I can get the hairs. See if I can focus that in, go out a little bit. So I got white rabbit fur, I got my balloon, and we can make the hairs move on the rabbit fur. So I actually got some nice static electricity. I've got the rabbit fur attached to my balloon here. And if that doesn't convince you about static electricity, I've got the age-old confetti situation. And I have my balloon. And we can get the confetti to jump from the paper, or from the bottom here, and stick to the balloon. So, Benjamin Franklin is attributed with discovering static electricity, but the Greeks actually knew you could take a rod of amber, do the same thing, rub it with rabbit fur, and we can do the exact same thing and play with static electricity. So while Benjamin Franklin sort of gets the credit, he certainly didn't discover it. It had been around there before. So we can also, so I've got this, we better see if we can get this to work. One of the things that we can do, we've got things running away, which is one of the things that we are trying to do, is that one of the things that we know, now did you guys just see what happened with my balloon?
It moved away.
Right? I've got a charged rod and the balloon is charged. I charged them both the same way, didn't I?
Yeah.
I rubbed them on the rabbit fur. My balloon is steady. I can actually move my balloon around, and I'm not even touching it.
So two charges of the same repel each other, right?
Charges that are the same repel each other. So in this case, we just presume that these are negatively charged, that I've brought the electrons to the surface. Now if I touch it, okay, I actually touch it, they definitely are going to have like charges, because I can charge by induction and I can charge by conduction. So we can move charges around by induction and conduction, And we can play with things there. So like charges repel, unlike charges attract. Okay, like charges repel, unlike charges attract. So the balloon and my rod are the same charge. Because well, now I'm getting some more attraction, so I've done something. But I get those different aspects of it. Thank goodness the building is dry, because I have tried to do that demonstration multiple times and I never get lucky. And that's always a wet day, and we don't get good static electricity on wet days.
Is the reason why that it's changed charges is because the distance between them?
Nope.
Why? You don't know.
No, I'll show you why it could change charge, but it has not. The charge distance between them is not going to affect the charge. Now, I can induce a charge, but the distance between them talks about what we talked about with Coulomb's law, and we'll get there in just a second. I'm going to throw away my little, so I don't create a huge mess in the room, throw away my little pieces, confetti pieces. Okay, so what we end up with when we do it, when I do an induced charge, if my balloon is positively charged, so we've got positive charges on my balloon, we're going to make that assumption for right now, and I put it up next to the wall, or I put it up next to something that does not currently have charge, because we've all done that trick, right? We've rubbed the balloon, created static charge, and we've put the balloon on the wall and it sticks to the wall. Everybody done that at least once or twice as little kids? Okay? What's happening is we induce the opposite charge to come to the surface of the wall. So the surface of the wall, we're getting those electrons to move to the surface of the wall, and we're going to get an attraction, which is going to hold the balloon to the wall. That's exactly what happens. Now, if we do the Van de Graaff generator thing, right? So if I put my hand on the Van de Graaff generator, what do we know happens to our hair? It stands up straight, right? It stands out straight. And if you are outside during a thunderstorm and your hair stands up straight, hit the ground. Don't stop to take selfies. Okay, don't stop to take selfies, because that means that you've got a charge in the air, and someplace along the way there's going to be a discharge, and a discharge of electricity during a thunderstorm is what?
Lightning.
Lightning.
If you're close enough to lightning, will will that happen?
You will feel your hair stand on end. I have walked across places and the hair on your arms will start to stand up, and it's like hit the deck, because there will be a strike, and a strike will be close. I have happened to have lived in two houses that have been, the lightning strike hit a tree in the backyard, and that was interesting because it actually came through. You could actually see the bolt come through and take out the color TV in the living room. That was, it disintegrated the tree in the back, and it took out the color TV in the living room. That was in Georgia during a lightning storm. And then I lived in a house in Edmond that we actually had lightning rods on the house that was hit by lightning as well. So I think I'm done with my lightning, thank you very much, but that's not necessarily the case. But you do get, if you are feeling it, it means that you've got an electrically charged situation, and that is dangerous. Like I said, don't stand there. I mean, you see it up on the mountains in Colorado, everybody's taking selfies. Come on, you're about to get zapped. So what's happening, so we're gonna do our hair situation here. If I put my hand on the Van de Graaff generator, I'm gonna be charged just like the Van de Graaff generator is charging, which means that these things are all going to be negatively charged. And because like charges repel, they're trying to get as far away from each other as they possibly can, which is what's causing your hair to stand up on end. because they're all the same charges and they're trying to get away from each other. One of the things that we do, there's a device that we have in the physics labs that has a metal piece, and at the bottom of the metal piece, it has pieces of either silver foil or gold foil. And if I bring an induced charge in, these things are all negatively charged, and they're going to repel each other, and you can get the foil to move by bringing the charged rod to it. And then once I touch it, I have created the charge and I've charged the system, then these things will stay apart because I now have the charge in the system, and they will actually stay apart. So we get charge, and we've played with electrostatics, and we know electrostatics, and we've had electrostatics, and we've done a lot of things with it. We play with cork dust, we've played with, we use it. What's a common place that we use electrostatics?
Ultrasound? No.
No. Think about window stickers. Plastic, the little plastic window stickers. There's no glue on them. They're not sticky, but they will stay adhered to the window, right? You'll even have them on your car. Those are electrostatic stickers. We're using electrostatics between the glass and the sticker in order to keep the sticker on. So that particular thing that we get that's there. So, a couple of things that we know now, which we didn't know back in the Greeks, and which Benjamin Franklin didn't know because it came along later, is we talked about conservation laws, right? We've talked about conservation laws along the way. And we have conservation of what?
Energy.
We have conservation of energy. What else?
Matter.
Mass. What else? This one comes in two forms, linear and angular. If I'm in my car and I'm not wearing my seatbelt,
Momentum.
And then I told you way back when that there'd be a fourth.
Charge.
Charge. And this one, and this one, and this one, we play with in general chemistry all the frickin' time, right? We play with it a lot. Now, we do in general, we don't necessarily do it in general chemistry, but if you go on to upper division chemistry classes, you will see momentum as well. That will come into how a lot of things are going to bond, how some of the bonds come into play. But most of the time we're dealing with energy, mass, and charge that we have. But we do have conservation of charge. So one of that says is that the net charge, okay, the net charge is going to be 0 if I have conservation of charge. Now when I'm inducing charge, like in my wall, I may be moving those charges to the wall, but the positive charges are going someplace further into the material. I still have a net charge of 0, just that I've moved my negative charges are out there. So we don't necessarily get there. We do talk about charge, right? Charge is going to be our lovely electron, which is positive. Our proton, our electron is negative. Our proton is positive. And we know the magnitude, right? 1.602 times 10 to the minus 19 coulombs is the charge on an electron. And it's also the charge on a proton, except the proton is positive. Some other things that we have to deal with. One are conductors. We've got conductors. Conductors are going to allow the flow of electrons. Which is why some of you defined electricity as the flow of electrons, but my conductors are, so let's look at the periodic table. I didn't happen to bring this piece of paper that has the periodic table, but there's my periodic table, which celebrated 100, or what is it, 200, anyway, its birthday was last week, again. Last year was the International Year of the Periodic Table. But what's the periodic table comprised of?
Elements.
Well, they're elements, but we divide our elements into 3 groups. What are they called?
Metals,
Non-metals and
non-metals,
metalloids.
Yeah.
metals.
Metalloids. Okay. And the periodic table is comprised, which one of those 3 groups comprise the most of the periodic table?
Metal.
Metals. Right? And if I draw it, here's my transition line. It's right in through here. These are my non-metals up here. My metalloids are right here. And the rest of this sucker are metals. Now, if I'm going to go pick up a good conductor, what immediately comes to mind as a good conductor?
Steel.
I've got steel.
Gold.
Aluminum.
I got gold. No, that's silver. That's gold. But silver and gold are both in there. Did I hear copper? Copper. What other ones?
Aluminum.
Platinum. Aluminum does conduct electricity. The reason we use it is because it's ubiquitous. But if I'm really wanting a good conductor, I'm in this spot right here, right? Now steel has in it iron, and it has, which is Fe, and it also has nickel if I'm going with stainless steel. And if I remember my parts on my periodic table, right? Let's see, it does A, G, A, U, and I think the last one, it goes N, it goes copper, Ni, so it goes copper, A, G, A, U, if I look at it in the line.
I think platinum's beside them.
And platinum's right in here, right? And this special block, depending on which periodic table you pick up, actually they give it its own column number. These 9 elements right in there gives you your own column number. And that's where my very bestest conductors are. They're my very bestest. All right? Are right in there. And that's something that we know from experience, that they're right there, that those are really good conductors. But let's go back to good old general chemistry. So here's my periodic table. Now when we deal in general chemistry, Gen Chem 1, right, these become our cations, right? And even all my metals become cations. And these are my anions over here, because they like to get electrons, right? Cations like to give up electrons, anions like to get electrons. And if I do these things, I get ionic bonds, right? They're bonded together due to electrostatics. So if I have sodium chloride, they're bonded together because my sodium atom is a positive, my chlorine atom is a negative, and they have a really nice attraction to each other. And if you're in my general chemistry class, we actually calculated the force that was holding those together. Okay, we actually calculated, which is why I can disregard gravitational force inside of an atom, because if I have a proton out here and I have an electron sitting out here orbiting, the electrostatic force between the proton and the electron is orders of magnitude greater than that of the force due to gravity between those 2 particles. So I can, and that's where one of the places Newtonian physics breaks down. Newtonian physics breaks down when I get really, really, really small. inside the atom. In Newtonian physics breaks down. I got to play with the electrostatics. Okay, I got to play with electrostatics and the forces that are involved there. So we know that this is an ionic bond. And then we talk about covalent bonds, and covalent bonds are between nonmetals and nonmetals, and what's happening in a covalent bond?
Sharing.
They're sharing. They're having a tug of war over that electron. Nobody wants to give it up. So they're going to fight over that electron. So the two types of bonding that we study a lot in Gen Chem 1 is ionic and covalent. And it's all about who has the electron and who wants the electron. But there was a third type of bond. Does anybody remember what the third type of bond was?
Like polar?
Metallic. No, covalent bonds can become polar, so that's not bad. That's not a bad guess, but it's a property of covalent bonds. But we talk about metallic bonds, and where do we say those metallic bonds show up? In the middle. The metallic bonds show up in the middle, and they show up in the middle because if we look at our orbital theory, right? Everybody remembers orbital theory. We just all go, oh, we don't like orbital theory. Okay, we got to deal with it. That these are the S bonds and these are the P bonds, and then we get the weird ones down here at the bottom, right? The weird ones down here at the bottom, those are the F ones, and we don't even want to go there, right? Only the strange people deal with those F bonds. But these are the D bonds. And if you can remember how many electrons can be in a D bond, that's 10. You can have up to 10 electrons in those suckers. And the other thing about those D bonds, if I look at my energy diagrams, those D bonds are so close together, I got some weird atoms in here that don't follow the rules. That they don't fill their orbitals right. And that's because the energy levels are too tightly bonded together. So if I come in and zap a copper atom with an electron, what's likely to happen? If I think about all those little electrons rotating around the copper atom like a solar system, and I come in with an asteroid, the odds of hitting another copper electron is pretty high, and I'm going to bounce it right out. Or I'm going to give it a photon of energy, and I'm going to bounce it right out. And so what happens in and metallic bonding is the copper atoms don't know whose electrons are whose, and they don't even care because they got so many electrons. It's just it's like fuzz on your shirt. Or if you live with a cat, it's like cat hair. You're going to leave them everywhere. So my metallic bonds have lots of free electrons that they can do things with, and that's what's going to allow me to be a good conductor. I'm going to be able to move those electrons around either by a potential difference, which is causing a force that's going to force those electrons to move, or by cascade theory, or by photons, or by all kinds of other stuff. I'm going to have lots of electrons that I can move around, which makes this part of the periodic table really good conductors. Now, aluminum is weird. It is a conductor. And it works as a conductor. The reason we use it, it's not necessarily the bestest conductor, but it's a ubiquitous metal. It's one of the most abundant metals that we have on it's not even really a metal, it's more like a metalloid, but it acts a lot like a metal. And it's most abundant on the planet, so we use it to make wire just because it's easy. And it's light. Okay, so it's easy and it's light, and so that gives it some material properties. It's also very ductile. One of the things about metals is that they're ductile. And if you've been following the news lately, there have been 3 different laboratories that claim to have actually produced hydrogen metal. They actually got enough hydrogen atoms so that it was in a solid state that they actually produced hydrogen metal. It's still speculative, but there's 3 labs that have claimed that they've done it, and they're showing pictures. And one of the other, there's another property of metals. What's the other property of metals? We've talked about ductile. We've got that they're good conductors, and they're good conductors of heat as well as electricity. What's another property of metals?
Malleable.
They're malleable. They don't break. That's part of their ductility. If I think of gold, what picture comes to mind?
Jewelry.
Okay, jewelry. Why do I like it? Jewelry.
Shiny.
It's shiny.
Oh.
It sparkles. And that is a property associated with the photon interacting with the energy states of the electrons. So it actually, that shininess that comes from metal, now, which is really interesting because if you think of pictures of sodium metal and potassium metal, you don't necessarily think of them as shiny. They really are, by the way. The reason we don't think of them as shiny is because we store them how? We don't think of them as shiny because A, that we store them in oils, because we don't want oxygen to get to them, and we don't want water to get to them, because if we get oxygen to get to them or water to get to them, we have what? A kablooey. So that's one of the reasons we don't necessarily think of those, even though if you really get into them and you cut them open, they are very shiny. They can be very shiny. But that is an interaction with the electrons and the photons, which is causing what's stuff that's shiny. So we have conductors. Conductors generate electricity, but then we have things that are not conductors, right? And those are called insulators. So we got insulators. Those do not conduct electricity. And remember, in chemistry, if I've got things that are good conductors, we call them electrolytes in solution, right? We have electrolytes. We can move electrons around. And one of the things that's weird about water is if I have pure water, it is not a conductor. I actually have to have ions in the water in order to get it. Now, the reason that we are worried about water is because it's real easy to get ions in water. It's really hard to get pure water. So, but pure water itself is actually a good insulator. But you can't get that, so that's why we end up with those other things. So good insulators are things like glass, rubber, styrofoam, things that are not going to conduct electrons. And they're not going to conduct electrons. We also have another class of materials. So we have insulators, we have conductors, and then we have something that we call semiconductors. And those we have to do things to deal with. We also have things like called superconductors, but when we're dealing with a superconductor, you usually have to get it really, really cold. Semiconductors, I have to do something to the material in order to get there. But all of these relate to the number of electrons that are free to move. I have to be able to move those electrons in order to get things. And we talked about charge by induction. So if I have something that's negatively charged and I have this as a neutral, this side's going to be positive and that side's going to be negative, and I'm forcing the charge to get there, I can have them neutralized. I can do charge by induction. If I touch them, that's conduction. And then if we talk about grounding, so I have a rod that's grounded, and usually we draw a ground. If I ever see an electrical diagram with that, that's a ground, because the earth is a huge charge reservoir.
Is that because of the magnetic field, or?
Nope, it's just the property of the material. It's just a huge charge reservoir. It's like your wall. You know, your wall can be a huge charge reservoir compared to the balloon. It's a charge reservoir. Now, we are kind of interesting because we are a rocky planet. So that's a good, magnetic field is going to be there. And why we ground is we want to reduce the probability of a spark. Because there are places that we don't want sparking to occur. So on a dry winter day, when you are filling your car tank and you're wearing your extra coat and you're going across cloth seats in your car, ground yourself on your car before you start pumping gas. I mean, because if you get a spark, that's what happens. Bad things.
Pumping with a flamethrower.
Yeah, I mean, bad things. So you watch those sparks. You try to avoid sparks. Car fueling is an example. One of the I think it was TWA flight over leaving JFK, or just before it landed in JFK, actually was a spark. It was an improperly ground in the fuel tank of the aircraft. Generated a spark, caused the fire, which took the plane down. Sparks, we don't like sparks, that's why we ground things. Okay, so most of us, we don't, luckily a lot of stuff that we're going to do in this particular part of physics, we don't necessarily go and derive, but we all have seen this one before. Force is equal to a constant, Q1, Q2, divided by R squared, where R is the distance between Q1 and Q2. This is Coulomb's law. That's Coulomb's law. And Coulomb's law, and we talk about field forces and we talk about contact forces, okay? Contact force is if I've got my little red wagon, or in this case my little black wagon, I can do a pull or I can do a push. And that's a contact force. But when we come into electrostatics, electrostatics is going to act more like a field force. And we're going to talk about electric fields. We're going to talk about magnetic fields. We didn't talk about gravity in terms of gravitational fields, but we know that that's there because remember Newton's law of universal gravitation. I've got a constant, I got a constant. Oh, I'm going to do this. I want to have these both together. Okay? I want you to look at the form of those two equations. Except for the fact that one's dealing with charge and one's dealing with mass, both the forms of those equations are identical. They're both going to behave as 1 over r squared, so I do have a distance effect on my charges. I do have a distance effect on my charges. The magnitude of my force is going to be highest as I'm closer to it, and it's going to fall off as I get further away. And that curve is going to go as 1 over r squared, whether or not I'm dealing with an electrostatic force or I'm dealing with a gravitational force. It's going to fall off as 1 over r squared. Now remember what happened with the intensity of sound. It also fell off as 1 over r squared. I have a lot of things that the intensity or the strength of it is going to fall off as 1 over r squared. Have an awful lot of things that do that. But the other thing is that these two equations look very, very similar. One of the big differences between these two equations is that charge can be positive or negative. And at least here on Earth, mass is only positive. Now, there's a bunch of physicists that are out there, again, natural philosophers, right? A bunch of physicists out there that are saying that antimatter is there because we can't, the mass of the universe doesn't seem to make any sense. And because if this is true, why wouldn't there be an antimatter? Physicists are looking for, there are a lot of physicists that are looking for the simplicity of the universe. And so if I've got this case and I've got this case, why can't the two cases come together? And so that's one of those ponder questions that, you know, when you're late at night and don't have anything else to think about, you can ponder that. That's not the one that keeps me up at night. I have two that keep me up at night. I personally do not like and have never ever liked the story of Horton Hears a Who. And it is a common theme. I can give you two other examples of the same theme. The galaxy in the cat's collar for Men in Black 1 and the subway locker in Men in Black 2. Those are all three of those are examples of Horton Hears a Who. Am I sitting on the Earth or am I sitting on the nucleus of an atom? Ponder that for a little bit. The other one that keeps me up at night, if we're an expanding universe, what are we expanding into? Those are two philosophical questions that I have to deal with. Those are mine, and then there's a bunch of people that are dealing with antimatter, and that's their particular philosophical question that they're trying to deal with. But what we're going to do is talk about these two, so I'm going to write these out a little differently. So I've got force, and this is Coulomb's law. And then this is Newton's. Okay, K, Q1, Q2 over R squared. And this is G, M1, M2 over R squared. Now, if I have a charge, I'm going to put a positive charge and I'm going to put a negative charge. This is my R, the distance between them. And forces are vectors, right? My force is a vector, so it's got magnitude and direction. I got magnitude and direction. And what we know about that is if I'm looking from this charge to that charge, that one's going to have that force going that way, and this one's going to have the force going this way. And the force, at least, is along R. My force is along R no matter what I do. The same thing that happened with our gravitational force. And remember way back when, you guys will remember these problems, right? Because you had one on the final. I got a big mass here, say this is 3m, and I got a little mass here, say that was 1m, and I had a mass over here, which was 2m. I had to find the center of gravity, for one thing, and I needed to know where the forces were. So if these things were, and in these cases, masses coming together, so these, you know, my force is going to go like this, and this force is going to go like this, and this force is going to go like this. And depending on if I looked at the net force on this charge, I had to account for those other two charge, or the net force on that mass, I had to account for the other two masses. Got to do the same thing with these. Except I got a problem. Okay? If it's positive and negative, it's going that way. But if I have two negatives, the force is going to go that way because they repel each other. I didn't have to worry about that before. I didn't have to worry about that at all. Didn't have to worry about that before at all. Okay, so let's do for grins and giggles. We're going to stick with good old Coulomb's law and Newton's law, and I'm going to give you some data. Charge is equal to 1.602 times 10 to the minus 19 coulombs. K, if you look it up, it's 8.99 times 10 to the ninth Newton meters squared, coulombs squared. And for most of the time, you can actually do this as 9 times 10 to the ninth. And I will tell you, if you want to write it down on your cheat sheet right now, you're probably going to want to keep those. But by the time you get through the end of the semester, those will probably be ingrained in your head and you'll never forget them. G is the one I can never remember. It's 6.67 times 10 to the minus 11 Newton meters squared, kilograms squared. And we will do the mass of the electron, it's 9
Is kilogram supposed to be squared too?
Yep, kilograms squared. I just didn't write it down. And mass of the electron is 9.11 times 10 to the minus 31 kilograms. Mass of the proton is 1.67 times 10 to the minus 27 kilograms. If I use the Bohr radius, that's 2.82 times 10. Oh, that's not the Bohr radius. No, that's not the Bohr radius. I want the Bohr radius. Bohr radius is of a hydrogen atom is 5.29 times 10 to the minus 11 meters. And if you want it, the radius I was writing down, this is the radius of an electron, is 2.82 times 10 to the minus 15 meters. And the radius of the proton is 0.833 plus or minus 0.101 times 10 to the minus 15. And that was measured on 9/6/19. And those are femtometers, if you want to know the actual prefix.
Femto.
Femto. F-E-M-T-O. Femtometers. But that's the current best estimate of the radius of a proton. Just so you have that data.
Zoe.
So if I want to find the force due to Coulomb's law, which I'm going to use as an E, that's the electrostatic force. This is going to be 9 times 10 to the 9th, and I'm going to have 1.602 times 10 to the minus 19 squared, divided by the Bohr radius, which is 5.29 times 10 to the minus 11 squared. That gives me 8.25 times 10 to the minus 8 newtons. That's the magnitude of the force between an electron and a proton in an atom, in the hydrogen atom. If I do gravitational force, that's going to be my 6.67 times 10 to the minus 11. My mass, 9.11 times 10 to the minus 31. 1.67 times 10 to the minus 27. Same radius, 5.29 times 10 to the minus 11 squared gives me 3.63 times 10 to the minus 47th newtons. What's holding the electron in a hydrogen atom is not a gravitational pull. You are 39 orders of magnitude different. 39 orders of magnitude different. The electron and proton do not care about gravitational forces whatsoever inside the atom. Not happening. So, a couple things you want to go back and review because it will help you out when you're working these problems, and for some of you with the other calculator, the calculator that drives me insane. You want to go back and look at if I have something times 10 to the 9th and it's multiplied by something times 10 to the minus 19 on top, that's going to end up being 10 to the minus 10th. Okay? If I have something that's 10 to the 9th divided by something that's 10 to the minus 19, that's going to give me something like 10 to the positive 28. You can review those in the appendix, how to work with your exponents.
So dividing by negative is kind of like adding by a negative.
Yeah. Yeah. It's you can manipulate them. Because what's going to happen to you is we're going to deal with, because of the size, as you guys just saw, we're going to deal with microcoulombs a lot, which is going to be something times 10 to the minus 6. And if I'm doing something with 3 microcoulombs, and I've got 9 times 10 to the minus 9th, and I have 3 times 10 to the minus 6, and I have 2 times 10 to the minus 6 for on top. Trying to put this into your calculator sometimes becomes a pain in the tushy. So this is easier to do 10 to the, I got minus 9, I got minus 6, so that's minus 12. This becomes minus 21. And then I've got 9 times 3 times 3, or 2. And that's a heck of a lot easier to deal with in my calculator. Particularly if you have that blue and white calculator. That blue and white calculator is a pain in the tushy to do exponents on. So as we get into this, it's going to become really important that you understand how to do scientific notation in your calculator. Either that, or you got to remember how to do this part. Okay? So you really want to kind of watch that aspect of it. All right. Okay. So we did that. Yeah, we're actually chugging away pretty good. Good for us. Okay, the other thing is you guys are working on homework, and you will have problems that'll be like this. My Coulomb's law is FKQ1Q2 over R squared, where that's the charge of one particle, this is the charge of another particle, R is the distance between them. You may end up having to calculate an acceleration. Remember, good old Newton's second law, mass times acceleration. So if I'm wanting to follow how a proton might be moving towards how an electron might be moving towards a proton, I may have to set these kinds of things equal. I'm going to go ahead and jump ahead just a hair, okay? I'm going to jump ahead just a hair, just so you guys can get extra credit on the homework and all that kind of stuff. I'm going to define the electric field. The electric field is defined as the force divided by the charge, which means that the electric field is going to be KQ over R squared divided by Q. This Q cancels. My electric field becomes KQ over R squared. Or I'm going to be able to write the force as Q times E. So if you're trying to jump ahead in the homework, this is how we're going to define the electric field. And basically where this comes from, this Q is something that we're going to call a test charge. And this is where we get to thank Ben Franklin for it. We're going to assume that the test charge is positive. It's like, give me a freaking break. Right? So gravitational force, if I'm doing this as G, we know that G goes like this, right? Around the Earth. It's always going to point towards the center. It's a field force. Okay? This is where Ben Franklin screwed us up. Okay? If I have a positive charge, we do it like this because we do a positive test charge, and if I take a positive test charge, it's going to move away from the positive charge. And my negative charge is going to have the field lines coming in like this because we've got field forces. So yes, this is one of those cases where Ben Franklin gave us, and as you guys have probably been doing in the lab or fixing to do in the lab, if I have something that's too positive and I have one negative over here, I can draw my field lines. They're always going to go from positive to negative, and how closely these lines are together designate the strength of the field. If I wanted to do just my typical dipole is going to look like this. And these are going to come in to the negative and away from the positive. So I can actually draw lines. And if I want something, we also talk about something that's perpendicular, and this is our potential lines, because we're going to talk about potential, light potential energy. But if I'm doing my lab where I'm mapping the electric field, what I'm actually mapping are lines of equal potential, and my electric field lines are perpendicular. I'm going to infer where my electric field lines are based on where I measure as equal potential lines. And if I do that, my equal potential lines around a dipole are going to look sort of like this. So I infer my electric field lines by looking at the potential, because potential is something I can measure. And my electric field lines are going to be pretty up there. One of the things is K. We've already told you that K is equal to 8.99 times 10 to the 9th Newton meters squared, coulombs squared. K is also equal to 1 over 4 pi epsilon, which is the permittivity of free space. And epsilon is equal to 8.85 times 10 to the minus 12 coulombs squared, Newton meters squared. And depending on which book you pick up, they may be working in epsilons. We will work in epsilons more when we get to magnetism. But depending on which book you pick up will depend on how they write out Coulomb's law. Whether they write it out with this K or they write it out with 4 pi epsilon.
Is it epsilon because of the elasticity?
It's permittivity of free space.
Free space, yeah.
Permittivity of free space. So it's a constant of the universe.
It's times 10, epsilon's times 10 to the negative what?
Negative 12. Catch it. That's a 12. It's negative 12.
I have 1 or 2.
Yeah, I was doing this weird. It's negative 12. And I think that's the best place to stop because I don't want to start a force problem. We'll do those on Friday, but that should give you quite a bit to get started on the homework.